Let's delve into the world of registers, specifically focusing on the parallel load register. We'll explore how flip-flops are used for multi-bit storage. A register is essentially a group of flip-flops that work together to store multiple bits of data simultaneously. Think of it as an organized container for digital information. It serves as an essential building block for temporary data storage in digital systems, holding information that the system needs to access quickly. Here we are looking at the basic structure of a register. Notice the arrangement of flip-flops. Each flip-flop is responsible for storing one bit of data. For example, we have bit 3, bit 2, bit 1, and bit 0, each stored in its own flip-flop. All flip-flops are connected to a common clock signal, labeled CLK, which synchronizes the operation of the entire register. The D and Q on the flip-flops represent the data input and output respectively. Now let's focus on the concept of a parallel load register. It's a type of register that can load all of its bits simultaneously in just one clock cycle. The key feature of this register is its fast data loading capability, where all bits are updated at once, making it efficient for many applications. Here is a circuit diagram of a parallel load register. Notice that each bit has a dedicated path. We have data inputs labeled D3, D2, D1, and D0. Each of these inputs goes through a multiplexer, labeled as MUX, and then into a D flip-flop or DFF. The output of each flip-flop represents one bit of the stored data. The entire register is controlled by a load control signal. This load control signal determines whether new data is loaded into the register or the existing data is retained. The operation of the parallel load register is governed by the load control signal. When load equals 1, the register operates in load mode. In this mode, new data from the inputs is loaded into the register, overwriting any previous data. When load equals 0, the register operates in hold mode. In this mode, the current data is retained in the register and remains unchanged. It is not affected by any new inputs. Here's how you might implement a parallel load register using VHDL, a hardware description language. First, we define the entity, naming it parallel_load_register. The port section declares the inputs and outputs. The inputs are clock named CLK load and data in a 4-bit standard logic vector. The output is data out, also a 4-bit standard logic vector. Next, the architecture section describes the behavior of the register. Inside the process, which is triggered by the clock signal, we check for a rising clock edge. If the load signal is 1, then the data in is assigned to data out, effectively loading the new data into the register. Parallel load registers have various applications in digital systems. Some examples include CPU registers, memory buffers, data storage units, and pipeline stages. In summary, the key takeaways are: parallel loading enables fast data transfer, and the load control manages register operation. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.